This talk will have basically two parts that are very different. The first half is kind of colloquium style. I think there's a lot of people that probably haven't seen me speak before, so I wanted to just give a sense about the types of questions I've been studying recently. And the second half will be kind of the most recent thing that we did, the kind of a technical lemma that is purely algebraic in nature, but has some important arithmetic consequences. So let me begin by stating the Brumer-Stark conjecture. Probably most people here haven't thought about it. So the setup is we have a totally real field, F, and we have a finite Galois extension that we assume to be a CM field, and such that the Galois group is abelian. Then there's some technical sets you have to define. The S contains the infinite places and the ramified places in this extension. So these are places of F, I should have said. So these are places of F that are either Archimedean or ramified in H. And then there's this auxiliary set T that you need, a set of, they're places that are necessarily finite because they're disjoint from S. And there's some technical condition on them that I won't give, but in particular, T is non-empty. And we define the L function of a character. So chi is a character of G. This is not stated. K is some complex character of G. And we have the usual L function defined by an Euler product, and we take it over primes not an S. And then there's this smoothing factor associated to the primes in T, and I'll just describe what role that plays later. It just looks very much like the Euler factor, except it's norm P to the 1 minus S rather than just minus S. Okay, this is some I think factor introduced by Deligne. Okay, so the Brumer-Stark conjecture states that with this notation, there exist certain P units in the extension H. So if we fix a prime P of F, maybe it's best to assume that this P splits completely in H, and we take a prime Gothic P of H above P, then the conjecture is that there exists a P unit with complex absolute value 1 under every embedding of H into C, such that the valuations of the conjugates of this unit at P, or equivalent, the valuations of U at all the conjugates of P, give you an L function evaluator. So if I take the linear combination associated to the character chi of the conjugate of the valuations of the conjugates of U, then I get the L functions for all the L values for that extension at 0. Okay, and this auxiliary T has to play a role because it's showing up on the left side, and the condition is that U has to be congruent to 1 modulo all primes above those lying in T. And maybe I can say a little bit about the role that this T is playing now, is that the right side is clearly an algebraic integer. It's a linear combination of roots of unity with integers. So the left side better be an algebraic integer, and that's the role that T plays when you introduce this smoothing factor of Deligne. Deligne and Ribet show that this is integral. Okay, so that's the Brumer-Stark conjecture, and I'm going to give you some history. So the story begins in 1890 with Stickelberger, who calculated the p-adic valuations of Gauss sums. So if the ground field F is Q and H is a cyclotomic extension, then you can write down certain Gauss sums in these extensions, and Stickelberger calculated p-adic valuations and basically proved the formula on the previous slide, that the linear combination of the valuations of the Gauss sums taken by a character chi give you the L functions of that extension. So this, again, goes back to the 19th century. Now, Brumer in the 1960s basically conjectured that units like this should exist when F is an arbitrary totally real field. Meanwhile, in the 1970s, or I should say a little bit later in the 1970s, Harold Stark stated a series of conjectures about units whose logarithms of their complex absolute values rather than p-adic absolute values are related, should be conjecturally related to derivatives of L functions of these extensions. And it was Tate who noticed that these are the same conjecture if you take, you can be stated uniformly if you take one place V, and if you specialize it to be a finite prime, you get Brumer's conjecture. If you specialize it to be an Archimedean prime, then you get Stark's conjecture. And what he realized that Stark has some extra conditions on his unit, which he translated basically into this statement that U should be congruent to 1 modulo the primes above T. And he said that should also hold in Brumer's context. And so he sort of combined the conjecture and called it the Brumer-Stark conjecture, even though, so this conjecture, as I stated it on the previous slide, is actually due to Tate. Okay. So let me give some motivation. So I think the question is interesting in its own right, but if you want further motivation for why we care about these units, we can talk about explicit class field theory. So I'm going to denote by FAB the maximal abelian extension of my number field F. Then the Kronecker-Weber theorem, very famous sort of classical theorem, states that when the ground field is Q, we can generate QAB by adjoining all the roots of unity. So from an analytic perspective, you could say if you take the holomorphic function e to the 2 pi I x, and you take the values of that holomorphic function at all rational arguments, then together they generate the maximal abelian extension of Q. Okay. And so, the Langlands program is about, writing down the representations of the Galois group of a number field. So the very simplest case of the GL1 case is what goes by the name of class field theory. So class field theory describes the automorphism group of the maximal abelian extension over F, so which is just inverse limit of the finite extensions. And the goal of explicit class field theory is to not talk about the one-dimensional representations of this Galois group or talk about the abelianization of this Galois group, but to talk about what is the field, what is the actual field FAB. So that's the goal of explicit class field theory. And so over Q, it's just described the way that I have already told you, that you take the holomorphic function e to the 2 pi ix and you plug in rational arguments. So the other context in which we know how to solve this question is when the ground field is a quadratic imaginary field. So if you take F to be Q adjoin the square root of a negative integer, then the theorem is that, so this Fn is the nth Ray class field, the Ray class field of conductor M, then it's obtained by adjoining the J invariant in an elliptic curve with complex multiplication by the ring of integers in F, together with essentially the coordinates of the n torsion points. There's some slight modification that you have to do called the Weber function, which I won't get into, but it's essentially the coordinates of the n torsion points of that same elliptic curve. Okay, so here J is the usual J function, it's a modular function, and so the basic takeaway from this theorem is that the role of the exponential function e to the 2 pi ix is played in the context of quadratic imaginary fields by these special modular functions, okay, the J function and the coordinates of these torsion points. So now Hilbert wanted to generalize this to arbitrary number fields. So in his famed ICM address of 1900, he stated in the middle of his list of 23 problems, the 12th, that we should generalize these results to arbitrary number fields. So these are some selected quotes that are kind of like specifically taken out to sort of advertise my results. But the theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. So that's the Kronecker-Weber theorem that I've already stated. Since the realm of the imaginary quadratic fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So at the time of Hilbert's lecture, the theorem about complex multiplication that I stated on the previous slide was not fully proven. And so it was in the works, and Kronecker sort of had these ideas, and he called it his Jugendtraum to kind of develop this explicit class field theory for quadratic imaginary fields. And this was eventually done later in the middle of the 1900s. But even at that time, Hilbert realizes that the extension of Kronecker's theorem to arbitrary number fields is of substantially more difficult problems. And he says, in the place of the realm of rational numbers or the imaginary quadratic field, any algebraic field, whatever is laid down, the realm of rationality seems to me of the greatest importance. Now, I kind of end the quotes here, but in Hilbert's actual problem, he's more specific about the type of solution he's looking for. He really wants something that parallels what I've told you about the case of Q and quadratic imaginary fields. He talks about special values of holomorphic functions with special transformation properties. Okay, so I'm sure he won't sort of accept the kind of description of construction of class fields that I'll be giving later in the talk. But so just to be more clear about what Hilbert was going for. Okay, so about why Brumer-Stark units might be interesting to you from this perspective is that you can basically show that if you take F and adjoin all the Brumer-Stark units, so for all primes P and all H, then you get, as long as you adjoin some special square roots, which are easy, just square roots of elements of F, then you get the maximal abelian extension of F. Okay, so basically the Brumer-Stark units generate these CM fields. So these square roots are just to deal with fields of arbitrary signature. But basically, if you take all the Brumer-Stark units, then you get the maximum abelian CM extension of F. Okay, so that's easy. This is easy to prove. This is not that deep. So if you care about class field theory, then you might say, well, it'd be great to know if these Stark units exist. And if they do exist, it'd be great to have a formula for them so that we could, an analytic formula for them so that we can use them to generate the maximal abelian extension of F. Okay, so now about that second question, I mentioned this earlier already. So my thesis was about to try to write down an exact formula for these Stark units in the case where you have a real quadratic field and P is an inert prime, and you have these sort of ring class field extensions. And so, so my advisors were Henri Darmon and Ken Ribet, and later I generalized this beyond the real quadratic case to arbitrary number fields and not just inert primes, but to arbitrary primes with joint works with other authors. So now we sort of have a conjectural exact formula for these Stark units in the extension. And so what does the formula look like? What's the flavor of the formula? It's given by a p-adic integral. So the conjecture is basically that the unit is up to a power of p, which you know because the Brumer-Stark unit conjecture, tells you what the valuations are supposed to be. There's these partial zeta functions. Just wrote that simply as zeta of 0. But what's the interesting part is what is the sort of p-adic part? And that is given by an integral, and it's just super simple integral from the right perspective. It's just the integral of the function x, and the depth is contained in the measure. So what measure are you integrating the function x with respect to? And this is a measure defined using the Eisenstein cocycle. So I could give us kind of a whole lecture on how to define the Eisenstein cocycle to make this conjecture more precise, but I just want to give you a flavor of it. It's just sort of some p-adic integrals with respect to some measure that you can write down explicitly. And I'll just say there's a lot of work on this Eisenstein cocycle. It goes, so my initial perspective is from Shintani's method due to, which was the cohomological formulation of Shintani's method is due to Solomon and Hugh, but there's many other perspectives from the topological polylogarithm due to Bailenson, Kings, and Levin. Czech has a really nice paper. So Pierre Charlois and I kind of did an integral version of Czech's method. And then really probably the original version where you integrate Eisenstein series, why it's called the Eisenstein cocycle, is due to Siegel. And that's been picked up very recently by a really interesting work of Bejan, Charlois, Garcia, and Venkatesh. It's his ongoing work where they are trying to now write down formulas for the Archimedean Stark units, so the Stark units rather than the Brumer-Stark units, using this cocycle. So this is kind of very much sort of still active work. And a point I want to make is this formula is actually explicitly computable. So I had a couple undergrads at Duke code this. So here's some examples. If you take f equals q join square root of 305, and this is the ring of integers, and you take the narrow Hilbert class field, so the conductor is 1, and you take p equals 3, and you do compute these p-adic integrals, you get 4 integrals, and you take their elementary symmetric polynomials, and you should be getting like honest integers, or maybe honest elements of this ring, I should say. And then so you just ask the computer, like you have these 4 p-adic numbers, take their elementary symmetric polynomials and tell me what integers they're close to. It kind of spits out these numbers, which are very small. The p-adic numbers have these like 100 p-adic digits. So then you guess that it's probably right. Sure enough, you look at this polynomial and you can check that it generates an abelian extension of this ground field with Galois group, Z mod 4Z, and it's actually unramified everywhere. So it's the right thing. And so here's a little bigger example. You can see the numbers get a little bit bigger. I just did this because it has degree 6. So this is the narrow Hilbert class field if Q adjoin root 473 and P equals 5. So this is really, these are just 2 examples. The students did thousands of examples and they posted it on some GitHub page. Okay, so what are the results I want to state today? So the first theorem is that the Brumer-Stark conjecture holds. So I proved this over Z bracket 1/2 a couple of years ago. So basically, you sort of show that there's a unit in the unit group tensored with Z bracket 1/2. We had sort of technical issues at P equals 2, which is what I'm going to probably spend the last half of the talk talking about. And so, yeah, the last half of the talk is about kind of the recent work, joint with Mahesh and 2 of my postdocs, Jesse Silliman and Jiuya Wang, where we got rid of these issues at P equals 2. And then the second theorem is that the conjectural exact formula for Brumer-Stark units that I told you about, at least qualitatively, this p-adic integral formula, that holds up to a bounded root of unity. And I should mention that a former student of Mahesh's, Matthew Honor, has gotten rid of this root of unity up to, I think it's down to just a plus minus sign at this point. And I think he's working on the sign. So almost have it on the nose. And so I mentioned this already. The Brumer-Stark units generate FAB, the abelian extension. So the two theorems together you can view as giving an explicit class field theory for totally real fields. Of course, it's not the final answer because we don't know how to prove, for example, Stark's Archimedean conjectures for these fields. So it's not like we completely understand these fields, but at least we have some way of producing these class fields via p-adic integration. Okay. I should mention there's refinements of the Brumer-Stark conjecture that we can obtain. So the so-called Equivariant Tamagawa Number Conjecture on the minus side, so associated to the CM abelian extension of a totally real field. And the idea of proving that is due to a very nice paper of Burns, Bullock, Dowd, and Seo, where they show that if you take my results with Mahesh and you look at them in towers, so we have certain theorems about fitting ideals of Ritter-Weiss modules, and if you look at those results in towers, then you can kind of patch those together to get the ETNC. So that this is kind of their idea. And now that we have the results on Ritter-Weiss modules over Z, that you can deduce the ETNC over Z. So you get kind of the full result. And I can say this has important implications. There's a higher rank version of Brumer-Stark due to Carl Rubin, which now follows from ETNC. There's a integral Gross-Stark conjecture, which follows from ETNC. The usual main conjecture of Iwasawa theory at p equals 2 was left open by Wiles. That now follows from ETNC. So we get all of those results as a corollary of our work. Okay, so this is, I think, the last sort of colloquium style slide. So this is just to give you a very quick rough overview of how we prove these results using Ribet's method. Okay, and here's Ribet in the center. There's maybe a picture from before I was born when he wrote this amazing paper on the converse to Herbrand's theorem, where he introduced this method to produce results about the relationship between zeta functions and class groups using modular techniques. So what is the method? So the first step is you realize the zeta functions or L functions as constant terms of Eisenstein series. Okay, so that's how you kind of introduce modular forms into the picture. You realize that your L functions are just one Fourier coefficient, the zeroth Fourier coefficient of Eisenstein series. Then you use manipulations with the Eisenstein series to produce Cuss forms. So the simplest analogy for this is just how do you define the delta function? You take E4 cubed and E6 squared, take Eisenstein series and manipulate them, and you take a linear combination to cancel out the constant term, and voila, you got a Cuss form. And it's sort of some generalization of that idea that allows you to go from Eisenstein series to Cuss forms. And the point is, the way that you do the manipulations is that modulo the L function, the Eisenstein series, is congruent to the Cuss form. Okay. Now, the reason we care about Cuss forms is that Cuss forms have irreducible Galois representations associated to them. Okay, so that's the link. This is due to, initially for modular forms over Q. This is due to Deligne. I should mention that I think Ribet's paper precedes that, so he actually produced the Galois representations he needed explicitly using the Jacobian of the modular curve. So he was working in weight 2, which made his arguments a little bit more complicated than we can now view them, where if you use arbitrary weight and you use Deligne's theorem, the argument simplifies a bit. Then you want to go from Galois representations to Galois cohomology classes. So when the Cuss form is congruent modulo, say an L value to an Eisenstein series, then you imagine that the Galois representation is congruent modulo L to what you get to the Galois representation associated to an Eisenstein series, which is the reducible representation. So the Galois representation that you get from this Cuss form modulo L, you expect to be reducible. And when we have a reducible Galois representation, you get associated to that a Galois cohomology class. So this procedure is called Ribet's lemma, and I'm going to speak at length about Ribet's lemma after this slide. So the whole talk will sort of zoom in on this little aspect of the argument in a moment. And finally, connection between Galois cohomology classes and class groups comes from, say, Kummer theory, class field theory. Okay. So that's Ribet's method, and I want to give sort of a hat tip to Barry Mazur, because I kind of stole this diagram from a beautiful lecture he gave at Ribet's 60th birthday conference, where he described Ribet's method and applications. Okay, so now this is the more technical part of the talk. So what is Ribet's lemma, and what is the so-called residually indistinguishable case that we've recently handled with Kakde and Silliman and Wang? So we start with some complete local Noetherian ring, and just for simplicity, I'll assume it's reduced in this talk. And we have a representation of a compact group into GL2 of the total ring of fractions, okay? And we don't know that the representation lies into GL2 of T, just into GL2 of the total ring of fractions, so that's very important. But we assume that the traces and the determinants of this representation lie in T, and moreover, the characteristic polynomial factors, modulo some ideal. Okay, so chi1 and chi2 are these two characters. And we assume that the characteristic polynomial of every element under this representation is reducible. Okay, and now we need an assumption, it's kind of a cuspidality assumption, that if you this K, because of my assumptions here, is just a product of fields. And if you take a projection onto any one of these fields, if you assume that the representation is irreducible, then the theorem is that there exists a finely generated T module and a cohomology class valued in M on which the group G acts via the character chi2, chi1 inverse, okay, such that the fitting ideal of M is contained in I. I'll define fitting ideals in a moment, but basically this condition means that sort of M is large. It's as large as T mod I in some concrete sense. Okay, so you think of like T as being ZP and I as being some ideal generated by P to the N, then that's saying that this M has size at least P to the N, basically. Okay, and what does the word surjective mean? This is maybe non-standard notation. What I mean is that if I take any representative cocycle, then the values of kappa of G generate M as a T module. So this isn't just like the zero class or something, right? It kind of generates. It's as big as this module is. This module is as big as T mod I, and this kappa generates the whole module. So it's not just some silly class. And that has to be true for every representative cocycle. Okay, so that's what I define to be surjective. And I'll mention, and this will come up later, I'll give the whole proof. So when Mazur and Wiles basically had to prove a version of this to do the main conjecture, they assumed that chi1 is not congruent to chi2 modulo the maximal ideal of T. So T is some local ring and has a unique maximal ideal. They assume that chi1 and chi2 are not congruent in the residue field. Okay, so that's what residually distinguished means. Okay, so I don't have that assumption here, so that's why I'm saying including the residually indistinguishable case, and that's kind of what's new and what I'm going to be talking about going forward. And I'll say that's why this is why the assumption P is not equal to 2 appears in Wiles' proof of the main conjecture, because chi1 is the trivial character there, and chi2 is a totally odd character. So they're distinguished by complex conjugation when 1 is not congruent to -1, so P is odd. So when P is 2, chi1 can be congruent to chi2, and then you have a difficulty. Okay, so let me define fitting ideal, because it plays a really important role. It was the last condition on the module M. So what is the fitting ideal of M? So fitting ideals are defined for finally presented modules over a commutative ring. So we take a finite presentation of it, and you take the ideal generated by all M by M minors of the matrix representing this map of relations. So M is the number of generators. Okay, and just as a simple example, if n is less than m, then the fitting ideal is just 0 by convention. There are no minors because the matrix isn't big enough. If m is equal to n, then there's just 1. It's just the determinant of this matrix. And in that case, the language is that m is said to be quadratically presented. And the fitting ideal then is just principal. It's just generated by the determinant of this one matrix. So what are some properties of fitting ideals? So just a simple example of the fitting ideal of R mod I. So there's one generator of R mod I over R, namely the number 1. What are all the relations? Are the elements of I? So the fitting ideal is just I. Okay, simple example. The fitting ideal is easy to see. Is a nice exercise. Show the fitting ideal is contained in the annihilator. So it's kind of a generalization of annihilator. But let me say one reason why it's better than the annihilator and why it's used and why it was really ingenious of Mazur and Wiles to introduce the study of fitting ideals into their study. And it's this last part they skip down, is that fitting ideals behave well with respect to base change. So basically, if you look at that short exact or that presentation, you can sort of tensor it with S, and it's easy to see that if you have an R algebra, then the fitting ideal of M tensor S is just the extension of the fitting ideal of R to S. Whereas annihilators don't have this property. So that's why fitting ideals are nicer in commutative algebra than annihilators, because they behave well with respect to base change. Now let me go back and tell you two other properties. This is good to give you an example in a sense of what the fitting ideal and the compared to the annihilators, what they are. If R is Z and M is a finitely generated abelian group, then the fitting ideal is 0 if M is finite. It's the ideal generated by the size of M. It's 0 if M is infinite. It's generated by the size of M if M is finite. So whereas the annihilator is like the exponent of M, and the fitting ideal is the size of M. So fitting ideal is like a generalization of size. Okay, and then another really important property is if you have a surjective map of modules, then you have an associated inclusion of fitting ideals. And that's also easy to see from the definitions. Okay, so now let's do Ribet's lemma in the residually distinguishable case. So this is the case of Mazur and Wiles, and this is profoundly important argument. This construction led to the whole theory of pseudo-representations, which has played a huge role over the past several decades since Wiles introduced it. So how does this work? So you know that chi1 is not going to go into chi2 mod M, so you start with that. You take a tau that realizes that distinguishability. By Hensel's lemma, this is a complete local ring. You know that row of tau has two distinct eigenvalues, since these are distinct. Call them lambda1 and lambda2. Okay, so then you choose the basis for your representation such that it's diagonal with respect to that row of tau is diagonal. So it has these two eigenvalues. Then you can get some information about a general. So I didn't say what A and D are. I should have said this. So then I write my representation as just A of sigma, B of sigma, C of sigma, D of sigma in that basis that I've fixed. Then the trace is A plus D, and you're given the assumption that the trace is congruent to chi1 plus chi2. Now, because of the special basis we've taken for tau, if you think about what row of sigma tau is, the trace of that is A of sigma chi1 plus D of sigma chi2, D of sigma chi2 of sigma. But of course, we have the same assumption about row of sigma tau, that its trace is congruent to chi1 plus chi2. So you have this congruence as well. Now you have two equations and two congruences and two variables. Think of A and D as my variables, and this first congruence and this last congruence, that's two linear congruences and two variables. So you can solve them as long as the system has non-zero determinant, but the determinant of the system of equations is like chi1 minus chi2, chi1 of tau minus chi2 of tau. So it's non-zero, so you can solve it. And if you solve it, you get that A is congruent to chi1 and D is congruent to chi2. So this is precisely where you use the fact that chi1 is not congruent to chi2. The fact that you can kind of solve these congruences to get congruences for A and D. So you get that A and D, first of all, live in T, in the ring T, rather than just the ring of fractions. And furthermore, you get a congruence for them. In the indistinguishable case, I don't know how to show at all that any elements like A, B, C, or D live in the ring T. Okay, I don't know how to get that for any basis. Okay. So there's something very special in the distinguishable case. Okay, but now that we have these congruences for D, we can try to define this cohomology class, this cocycle. You let B be the T module generated by the B values, the upper right-hand corner values. And then you just write the representation equation, B of sigma tau equals A of sigma B of tau plus B of sigma D of tau. That's just how you multiply matrices. And if you reduce that mod I, so this is, when I say mod I, this is like mod IB. So this is in B mod IB. You have B bar of sigma tau is chi1 times B plus B bar of sigma times chi2 of tau. If you scale that, so I guess you scale this equation by chi1, chi2 of sigma inverse, I think, then you see that the function you get kappa by scaling B becomes a cocycle. This is basically looks like a cocycle equation, right? If you scale it properly, then you get the exact cocycle equation. So that's your module M. It's just B mod IB. The irreducibility assumption on B implies that B is a faithful T module, and just by the properties, the fitting ideals that I gave you, respect space change and that is contained in the annihilator, those two properties together tell you the fitting ideal of B mod IB has to be contained in I, because B is a faithful T module. Okay, so one thing that I want to point out is kind of like the hard part of this argument was kind of getting figuring out how to construct this module, taking this special basis, and then proving you have a cocycle. And then kind of the easy part of the argument is showing that the fitting ideal is contained in I, because this part is easy just because of functorial properties of fitting ideals. I mean, the hard part is thinking of that you should be using fitting ideals, which Mason and Wiles realized. Okay, so right. So now when we go back, this is the same slide I gave earlier, restating the theorem. But now we're not going to have the assumption that chi1 is not congruent to chi2. We're going to basically go forward assuming that chi1 is congruent to chi2. And I guess one of the insights that we had is to what type of module to make, which is no restrictions. That is, people often try to construct like a free T mod I module or some module of the form B mod IB. And so we just some module. And just realizing that the condition that you want to prove is just that fitting ideal is contained in I. That's all you care about. Right? So that maybe with a little bit of insight is just the statement that we're trying to prove in this context. Okay. So I'm going to talk about how to prove this now through the rest of the talk. Okay. Actually, before I say that, I should mention that very interestingly, as we were doing this, concurrently there was work of Ofer and Weiss, Amit Ofer and Ariel Weiss, who were studying a similar question, and they're restricting the case when T is a DVR. And I was very interested by their paper, and I had an undergraduate from Barcelona visiting me doing his senior thesis named Rafa Hajar Munoz. And so he gave him as a problem to deduce the theorem that I just stated on the previous slide from the works of Ofer and Weiss in the case when T is a DVR, and he was able to do that. So the DVR case is kind of handled by sort of studying the Bruhat-Titz tree of GL2. But the general case is a bit more difficult, so I want to explain how you do that. So kind of on the flipping the Maser and Wiles construction around. What's easy now is to define the module and to show that you have a cohomology class, and what's hard becomes proving the fitting ideal construction. Okay, so we don't choose any special basis. It doesn't matter what basis you choose. Kind of a basis-free construction. So first of all, you extend rho from a group homomorphism to a T algebra homomorphism from a T bracket G, which is the ring of 2 by 2 matrices over K, and then you define delta I to be kind of the image under rho of these sort of twisted augmentation ideals. So you look at G minus chi I of G, and you look at the image under rho of those. So this is kind of a scalar matrix chi I of G here, and you call that delta I. So just to give you, okay, let me move to this one because that one's shaking. So, and from experience, it's going to be shaking for like 10 minutes now. There's a lot of inertia there. All right. We should model the swaying. Okay, so, all right. So if chi's are trivial, and that's a perfectly reasonable case to consider, if the chi's are trivial, this is just the augmentation ideal, rho of G minus 1. And you're looking at the image under rho of the augmentation ideal. And then this would be the augmentation ideal modulo its square. And as many of you probably seen before, the augmentation ideal modulo its square of a group is just the abelianization of the group. And if you think about it, that's what we're trying to prove. We're trying to construct a class, an H1 of G acting on some module. But if there's no action, if chi1 and chi2 are trivial, then H1 of G is just a homomorphism from the abelianization to the module. So you're basically trying to get the abelianization if you want the kind of universal construction. So that's why it's natural to construct this kind of I mod I squared. And this is just the generalization when you have arbitrary characters. Okay, so if you define this delta 1 mod delta 1 delta 2, then there's a canonical cohomology class valued in there, which is just the image of G, basically like rho of G minus chi1 of G, that by definition lives in delta 1 and you scale it appropriately, then it's an easy exercise to show that if you write down the condition of a cocycle, sort of chi of G1, G2 minus, the appropriate linear combination of, kappa of G1, G2 minus the appropriate linear combination of kappa of G1 and kappa of G2, that difference turns out to lie in delta 1, delta 2. It's almost like how you think of defining delta 1, delta 2. Okay. All right, so that's easy. So now we've done most of the work of the theorem, or of the statement of the theorem. We have a cohomology class. It's defined in this module, and it's easy to show that it's surjective in the sense that, right, M is the quotient of delta 1, and these obviously generate delta 1 because that's the definition of delta 1. It's the thing generated by these elements. So, and then there's some Nakayama argument to show that it's true for any cohomologous cocycle will still generate. That's just Nakayama's lemma. So most of the statement in terms of words of the theorem have already been proven. But the hard part that takes the rest of the time is the fitting ideal computation. So how do you calculate the fitting ideal of that? Okay, and this was a really exciting project. It took a really long time, was to compute the fitting ideal of this module. And that's what I'm going to spend the rest of the talk talking about. So you want to prove that the fitting ideal of this module that you've constructed lives in I. So in notational simplification, I'm going to basically reduce the case I mentioned earlier, where chi1 is equal to chi2. You can even further assume they're both the identity. It's not going to really change anything. Generalizing to the general case, once you have this general construction, is just notation. All the ideas are already present if you specialize chi1 and chi2 to be equal, even if you specialize them to be identity. The difficulty of the problem is still there. Okay, so M is just this delta 1 mod delta 1 squared. So if you take generators of delta 1, then what you need to mod up I to get M, you just need to take all products and then write them as linear combinations of the original generators, and those are your relations you need to mod out by. Now, these row i's are just taken to be generators of delta 1, and delta 1's not necessarily free. There might be relations amongst the row i's, so you have to worry about those too. So there's two types of relations you have in your module, right? So these types of relations, I call these delta type and these epsilon type relations. And so what is the definition of the fitting ideal that it gave earlier? Is you here or here? Which one? Which equation are you talking about? In the second one. In the second one, good question. There's no I. Yeah, there'll just be a relation. The sum of epsilon, right? I guess I would say that the ith relation is this. Yeah, sorry, but I didn't do that here. So you're right. You're right. This is bad. It should just be the sum of epsilon j rho j. Thank you. Yeah, they're just saying there's some coefficients and there's some. Yeah, I don't need the I. Okay. So, so the fitting ideal is just the ideal generated by determinants of R by R matrices D, where each row is one of these relations or one of these relations. Okay, so now where do you get elements of capital I from? Like, how are you ever going to show something lives in capital I? Well, that's given by our assumption. We know that the trace of rho minus 2 chi of G. So I said chi1 and chi2 are equal. I'm going to call it chi. Okay. So the trace of rho of G minus 2 chi of G is an I, and the determinant of chi of G minus chi squared of G is an I. Okay. It turns out, so it's pretty simple to see that these facts imply that the trace and determinant of any element in delta 1 lives in I, right? So like delta 1 is generated by things like rho of G minus chi of G, and this is exactly saying that the trace of rho of G minus chi of G is an I, right? And similarly for the determinant. So this is an easy thing to check, that the trace and determinant of anything in delta 1 lives in I. So that's how you're going to get elements of I. Okay, so so to prove this, we work in a polynomial ring. Okay, so we're working a polynomial ring. So because we want to show certain sort of algebraic relations, basically we want to take this fitting ideal, it's this big R by R determinant, and we want to somehow show that it can be expressed in terms of traces and determinants of elements of our elements in delta 1. Okay, so so it's this kind of a polynomial manipulation. So it helps to work in a polynomial ring rather than this concrete ring T that has actual elements, and treat everything like a formal variable. So we take this formal polynomial ring and these coefficients delta I. And I think for the rest of the talk, I'm just doing delta type relations because in fact, the epsilon ones are easier to deal with. So let's just deal with, say I have R delta type relations. And then again, these are all formal variables now, AEI, BI, CI, DI. And then I have this ideal J, which is the things I'm modding out by, which is rho I, rho J. So this is shorthand notation for, okay, each of these represents 4 equations. That is, I'm modding out by rho I, rho J equaling this thing. So that's 4 equations for the A, B, C, and D coordinates. So ideal J is generated by 4 R elements, okay? I have R relations like this, and I have four relations for each such relation. Okay. So I'm not going to get it. I can't get into all the details, but it turns out. So the point is you have a homomorphism from R mod J to K, right? You can just send every one of these formal variables to the thing that it represents in K, okay? And you want to show somehow that your fitting ideal in here lands inside of I, right? So it turns out that there is a kind of an adjustment you can make to your determinant D to get something called D prime, where the determinant of D prime is actually 0 in K. Okay, and so therefore it suffices to show that the determinant of D minus determinant of D prime maps to I in here because determinant of D prime goes to 0. Okay. And so what you want to show is that in this ring R mod J, this thing that you have, determinant of D prime minus determinant of D, can be expressed as a polynomial in the traces and determinants of matrices in the algebra generated by the rho I with coefficients in R0 and no constant term, because each such trace and determinant, I told you, lands in I when I map it forward by this homomorphism, okay? So then the question becomes, how do you take an element of R mod J and show that it can be expressed in terms of polynomials and traces and determinants? And for this, there's a beautiful theory that I discovered that I had no idea about, but I discovered it, trying to do this work, which is, I actually discovered because there was a math overflow question that asked this question, like, how do you determine the invariance of this ring? And someone said, you should look at this book. So then I looked at this book. And this book says the natural thing that you would expect is that and this is why you want to pass rings of formal variables, which says that if you look at the ring of invariance under the subring under conjugation, then you get the ring of traces generated by the trace and determinants in the algebra generated by all of the matrices rho I. So if you were working in R rather than R mod J, you would just need to show that your element is invariant under conjugation. Okay. Okay, so now rather than working with invariance under GL2Z, it's better to work with the algebraic group GL2 and use what's called rational cohomology. So rational here refers to rational functions, not the rational numbers, which is kind of the action of the algebraic group rather than its physical group of points, GL2. And the reason for this is that in rational cohomology, restriction to the Borel is an isomorphism on cohomology, where that's not true in sort of, GL2 restricting cohomology from the group GL2Z to, the upper triangular matrices or something. That's not an isomorphism on cohomology, but it is in the world of algebraic groups. Okay, so what are we trying to do? So we have some element in R mod J, and we want to show that it's in the image of the ring of traces and determinants. And we have this theorem that says the ring of invariance of R is the subring of traces. So what we're saying is if you have an element that's invariant here, then if you push it forward under the connecting homomorphism associated to the short exact sequence, you want that to be trivial so that it's in the image of this map. Okay, so we have some element in R mod J, and we're going to push it forward to the first rational cohomology, and we want to show that it vanishes so that it lies in the image of the invariance, which by the theory of matrix invariant theory, due to De Concini and Processi, that it's the ring of traces and determinants. So we'll be able to apply that theorem if we can show that the cohomology class associated to this element gives rise to the trivial class in H1. All right, so that's what we're down to now, is proving that this cohomology class vanishes. Okay, so what's important in this is that the class actually arises from a smaller ideal. That is, when you show the invariance, so I had some element of R mod J, which I called determinative D prime. I didn't explain to you that somehow you can show that it's B invariant. It's invariant under this Borel. I haven't given you that proof, but it turns out that in showing that result, there's a smaller ideal that you can take rather than all of J, which is J was the ideal generated by sort of all four coordinates of these matrices. It turns out that you only need to use the B components of these equations in order to get the invariance. Okay, so let's call these B components of these matrices, call them B1, capital B1 through BR. And so J prime is the ideal generated by B1 through BR. And it turns out that the element that you want to show is actually coming from traces and determinants, that it's actually invariant modulo J prime. Okay, and so your class in H1 of Bj actually is the image under the natural push forward from J prime of a class in H1 of Bj prime. And so the way that we're going to show the vanishing of this beta 1 actually has nothing to do with our particular class. We're just going to show that the push forward map from H1 of Bj prime to H1 of Bj is the zero map. So just the fact that your class actually arises from a smaller ideal is enough to give you that the H1 class vanishes. Okay, so for this vanishing, we're going to have to kind of lift this cohomology class from H1 via the Kosel complex. So if you look at the free Z module generated by these B's, okay, it turns out that the B's generate a regular sequence in the ring R, and so the Kosel complex that you get from this free Z module, this free R module, once you tensor with R, is exact. Okay, so that's a condition on when the Kosel complex is exact, is when the generating sequence is a regular sequence. Okay, and this is the usual Kosel complex. So the maps are just given by kind of dropping one element down and taking the usual linear combination. Okay, so this is an exact sequence. Okay, and the purpose of this is this allows you to lift your cohomology class. Okay, because the point is we want to eventually show something zero, and if you can lift it all the way up here, it's clearly zero because there's a zero at that. The Kosel complex ends. so that's going to be helpful for us. So okay, so the image of this map F1, the last term, the Kosel complex, is the ideal generated by the BIs. And so we had a class in H1 of Bj prime, so we can view that as H1 of the image of F1. Okay, but then you have a short exact sequence by the exactness of the sequence. So right, the kernel of F1 is the image of F2. So you can then use the connecting homomorphism associated to your cohomology class to get a class in the H2 of the image of F2. So continuing in this way, you get classes alpha I and the HI of the image of Fi. And as I said, the last class, alpha R plus 1, is zero because it lives in the zero, lives in the zero module because the complex ends at some point. Okay, and now the punchline is that you can embed your Kosel complex into a bigger complex, and it turns out you can embed it into a complex where these terms down here, so this is not an exact complex anymore, but you can embed into a complex where the terms are acyclic. It turns out that these are direct sums of copies of the adjoint representation, and it's comes from the theory of algebraic groups that the adjoint representation has trivial cohomology, and in fact, any tensor product of the adjoint representation with itself and the ring R itself all have trivial higher cohomology. Okay, so then if you push forward your classes here, alpha I, you get classes that we call beta I. And you remember the push forward of alpha 1 was the class we wanted to show that vanishes, the class beta 1 in H1 down here of J. So I was trying to show that this push forward map is zero, but I have classes H in HI of each of these terms, and I can push them down to classes that I call beta I. Okay, and now you're ready to finish the argument. So alpha R plus 1 is zero because it's just zero here. So beta R plus 1 is zero. But what are these betas? Remember, these were coming from connecting homomorphisms, right? So if something is zero under a connecting homomorphism, that means that the thing that it came from lifts, right? So beta R plus 1 being zero means that beta R lifts to a class in the HR of WR. But this cohomology group vanishes because I said this was acyclic. So this is 0. So that means beta r is 0. But so now you see I've gone from beta r plus 1 being 0 to beta r is 0, and then this continues. So the fact that beta r is 0, beta r, right, this is something coming from a connecting homomorphism. So the fact that it's 0 means that the previous cohomology class lifted. So beta r minus 1 lifts to wr minus 1. But this wr minus 1 is acyclic. So if it lifts, right, so this cohomology of this whole group is 0. And so if something lifts to 0, that means it is 0. So beta r minus 1 is 0. And that continues downwards. So that cascades downwards until you get all the way down to j, and you get beta 1 and 0. So we kind of start with alpha 1, and we lift it all the way up here. We pushed all the way down, and then went all the way down. And that's how we got 0. So that was kind of a nice argument. And that's the end. Thank you. Yeah. Like what it is? Yeah. Yes. Yes, it is actually. So I'll just say that what was going on here. So V is the direct sum of copies of the BIs, right? Right. But BI is a matrix. So you have an A, B, C, and D. So you just take the wedge product of, so WR is just the wedge product of a direct sum of copies of the adjoint, like getting all A, B, C, D together as copy of the adjoint, because it's like the whole matrix and the action is conjugation. So, okay. And so you take so it's not the full wedge product. So when you expand by, like, I guess it's the Kuhn formula, the wedge power of a sum, you get sums of tensors or what, right? But you only need where each term occurs once, because kind of this is, right, how to say, this is like one dimensional. So you can't have one BI showing up more than once. You get like BI wedge BI B 0. So so you get different distinct copies of the adjoint, and that's what the W is. It's just the sum of the distinct copies of the adjoint tensored together. And so that's why it has trivial cohomology, because the adjoint has trivial cohomology, and it is called having a good filtration in the theory of algebraic groups. The adjoint has good filtration. The set of things has a good filtration, is closed under tensor product. So any tensor power of the adjoint also has trivial cohomology. Yeah.
Can you just say a brief word about how you get from this precise form of Ribet's ladder to Brumer-Stark?
Okay, so there is a module that represents the functor of receiving cohomology classes under certain local conditions. So I didn't say anything about local conditions, just the global picture. And so it's, half of the work is doing the local picture. But let me put that aside and saying, if you have a Galois cohomology class that satisfies certain local conditions, then there's a homomorphism from a certain module called the Ritter-Weiss module to your module. So the fact that our fitting ideal is contained in I implies that the Ritter-Weiss module's fitting ideal is contained in I, because one of the properties of fitting ideals that it gives, you have a surjective map. And that's why we need our cohomology class to be surjective. So if you have surjective cohomology classes, then you have a surjective map for the Ritter-Weiss module. The Ritter-Weiss module is basically like the class group. It sits in a short exact sequence with the class group, and so you get information about the class group from this fact. You're basically showing the class group is as big as you think it is, and the class group is related to the Brumer-Stark conjecture. Brumer-Stark conjecture can be kind of reinterpreted in terms of saying that the Stickelberger element annihilates the class group, and that follows from this fitting ideal statement. In fact, I guess something a little bit stronger is that the Stickelberger element not just annihilates the class group, but actually is in the fitting ideal. As I mentioned, fitting ideals are contained in class annihilator, so it's a refinement. For the experts, I kind of mistook. It's in the fitting ideal of the Pointryagin dual of the class group, sorry, which is an important point in the theory. It's discovered by Popescu and Kurihara.